Hello, this is Mrs. Huntley. This is Module 3, Lesson 1, What Lies Behind the Same Shape. You should be on page 1 of your new module, and the essential question for this lesson is, can something be the same shape but not the same size? So this exploratory challenge is meant for you to do kind of on your own. I'm going to walk through it with you a little bit, and then I'm going to release you to be on your own for a little bit. The exploratory challenge asks us, or tells us, two geometric figures are said to be similar if they have the same shape but not necessarily the same size. Using that informal definition, are the following pairs of figures similar to one another? Explain. So pair A, we've got two triangles. One is smaller, the other one is a little bit larger, but it looks like our angle measurements are the same. So I'm going to say that these are similar. They're the same shape, but a different size. Pair B, I have a square and I have a rectangle. A square and a rectangle. Squares and rectangles are different shapes. So these are different shapes. One's square, one's rectangle. They are not similar. Okay? Pair C, we have two pentagons. They're exactly the same size, exactly the same shape, so they are congruent. Pair D, we've got two circles, one's larger than the other one. Again, same size, or same, I'm sorry, I misspoke. They are similar, they are the same shape, but a different size. So, again, if something has, something that is the same shape, but not the same size, we call it similar. It's not the same, but it's similar. So what I'd like you to do right now is pause the video, look at pair E, F, G, and H, and based on that definition alone, tell me whether these shapes are going to be similar or not similar. So go ahead and pause the video right now, and then come back and check your work. Pause it. Okay. Pair E, same shape, different size. These are similar. Pair F, same shape, different size. Again, these are similar. Look, we've got two circles. We've got two eyes in both the circles, and our mouths are facing in the same direction, so those are the same shape. The next one, you might have looked at it and went, oh, these are the same, because I can tell that this one was just knocked down or something like that. It looks like this one is sitting upright and that one is knocked down. But look at the outline. This one is a circle. This one is an oval. So these are different shapes. They are not similar. Pair H is probably confusing to you. These are two parabolas. They are actually the same shape. They are both parabolas. This one was just multiplied by a scale factor, which is what makes it look flatter than the other one. But they are indeed the same shape, so these are, again, similar. Oops. That's weird. Oh, I can't spell. Shame shape. Okay. I am challenged right now. Different. There we go. Different. Similar because they're the same shape, but they're a different size. Okay. Next, we have a new notation. Oops, I almost did the same thing again. Hang on a second. We've got some notes at the bottom. So similar means same shape that has been dilated by some scale factor. Everything grows according to the scale factor, so it's proportional. When it gets larger or smaller, everything stays in the same proportion. A dilation is a transformation that moves points in the plane according to the scale factor. And we're going to use R as our variable to represent the scale factor. R will either enlarge or shrink our figure. So here's some few rules about scale factor. If the scale factor is 1, the figure stays the same size. think of something being multiplied by 1. It stays the same value. If the scale factor is greater than 1, the shape will be enlarged. If the scale factor is less than 1, the shape will be shrunk. The scale factor cannot be negative. You can't grow something by a negative rate. So scale factors that are less than 1 are going to be greater than 0. So it'd be greater than 0, less than 1, and that means it's going to be shrunk. So that would be like a fractional scale factor. Alrighty, let's move on. I'm going to teach you a new notation. So when you have these vertical lines on either side of your segment length, that means the length of that segment. So if I have this notation with this vertical line before and after OP, that means the length of OP. So if I'm given a length of OP at 5 inches, and then my directions tell me that segment OP is dilated by a scale factor of R equals 4, what is the length of segment OP prime? This is the rule that we're going to be using, or this is how we're going to figure it out. So OP prime is equal to the scale factor times the original length of OP. So OP prime is equal to our scale factor is 4. So 4 times the original length, which is 5 inches. So OP prime is going to be equal to 4 times 5 is 20 inches. Okay, it is a multiplicative relationship. I'm going to be multiplying things by the scale factor. So if OP is dilated by a scale factor of 1/2, what's going to be the segment of OP prime? So again, we're going to start with our rule. OP prime is equal to the scale factor times the original length of OP. So OP prime is going to be equal to 1/2 times, they said it was 5 inches. 1/2 times 5. 1/2 times 5 is going to be 2.5. So OP prime is going to be equal to 2.5 inches. Okay. It says next, let's move on. Use the diagram below to answer exercises 2 through 6. Let there be a dilation from center O. Then dilation P equals P prime and dilation Q equals Q prime in the diagram below. OP is 3 centimeters and OQ is 4 centimeters as shown. And you're going, wait, what? Okay, we've got this drawing here. Okay, it's telling us OP, this length is 3 centimeters. OP prime, whoops, OP prime, we don't know that length. It's not given to us. Okay, OQ, 4 centimeters. OQ prime, not labeled, it's not given to us. But what is given to us is there's a dilation. Oh, no, it hasn't been given to us yet. Okay, so if the scale factor is 3, what is the length of segment OP prime? So this one. So OP prime is equal to R, scale factor of 3, times the original length, which is 3. Right here. That's where I got that from. So OP prime is going to be equal to 9 centimeters. If the scale factor is 3, what is the length of OQ? Oh, this should say, wait a minute. This should say OQ prime. Okay. If the scale factor is 3, what is the length of segment OQ prime? So OQ prime is going to be equal to 3, our scale factor, times the original length of OQ, which is right here, 4 centimeters. So OQ prime is going to be equal to 12 centimeters. Again, it is a multiplicative relationship. Excuse me. I'm going to skip this because I already used the definition when I was figuring it out. This is what they mean by the definition. So OQ prime is equal to R times the original length of OQ. I kind of set it up that way. So I'm looking at these next few problems as being kind of redundant. So we're going to just skip those for right now. So let's go down to 7. If you know that OP is 3 and OP prime is 9, how could you use that information to determine the scale factor? Now, you might be going right off the top of your head that you know it's 3 because it was given to us as 3 earlier. But let's take a look at how I would figure this out mathematically. So if OP prime is equal to our scale factor times the original length of OP, we can plug in what we know and solve for what we don't know. So if OP prime is 9, and we don't know our scale factor, we'll pretend we don't know our scale factor, and we know that OP was 3, now I can solve for R. And how would I do that? I would divide this side by 3, divide this side by 3, and then I'd be left with R all by itself on the right. 9 divided by 3 is 3. So R would equal 3. We already knew that because we knew the answer kind of off the top of our head. Another way that you can remember this, and this is how I learned, is you're always going to have your image divided by your pre-image to figure out your scale factor. So new divided by old equals whatever you multiplied the old by. Hopefully one of those two will help you, and this will become more familiar as we're moving on. So in summary, a dilation will enlarge a figure when the scale factor is greater than 1, and a dilation will shrink a figure when the scale factor is less than 1 but greater than 0. If we multiply the segment length by the scale factor, I don't know why that's a C-A-L-E scale factor, we get the length of the dilated segment. This notation, that line with OP inside, means the length of OP. If we multiply it by the scale factor, we get the dilation. And here's the rule that they were talking about, or the definition. So OP prime is equal to the scale factor times the length of OP. Okay. Have a great night, and I hope you know that you only had to watch this video if you were absent and didn't get the lesson in class. If you watched it, I hope it was a good refresher and that you had complete notes. I'll see you tomorrow.